Hey, what is up, the people? All right, so I know that there's probably going to be some people here that stumbled across this video looking for how to replace the OLED inside of the meter here and want to hear me waffle on about a bunch of other random stuff. So if that's you, that's the case, don't worry about it because I got you, fam. Just go ahead and go to whatever time I put over here, and that's where I'm going to start actually doing like the physical work of replacing the screen from the board that it's on. But for everybody else that's here to hear me waffle on and just go on about random crap, well, you know what to do. You're already doing it. Okay, so if you've been watching my channel for some time, you know that the OLED display inside of this thing has like slowly been just fading away and getting dimmer and dimmer, and now it's to the point where you can't like see it like at all. Like that's on. You might have heard the beep there, but it's just not visible. But the OLED itself is not dead. I was actually able to take my Pixel 7 Pro and put it in the night mode where it tries to capture as much light as possible. And I put it in the garage in a little stand and everything because you have to like hold it like completely still. And it's actually able to, like see what still shows up on the display. So yeah, it's not dead. It's just totally useless. So I did try to do like a little bit of a voltage mod on the display or on the board that has the display on it to try to boost up the voltage that the driver uses to power the LEDs. Or yeah, because it's like a bunch of tiny little LEDs. So to pump up that voltage a little bit, and it kind of worked, but it wasn't enough to make like a huge difference, and it just yeah, it didn't quite work out. So I ended up reverting those changes and put it back to stock. So I had actually been doing some experimenting with this, trying to find like a replacement OLED screen that I could use because unfortunately the original one that was used inside of this thing is no longer manufactured, and so yeah, they're like impossible to find. But however, there are other displays that are made that are the exact same resolution with a very similar chipset, and I was trying to see, if I could get like one of those to be like compatible with this. I'd been going through the data sheet and all that stuff, but while I was doing that, I was trying to find to see if I could find some bad units on eBay or whatever, so I experiment with and not risk damaging this one while I, try to find something compatible. When I came across a replacement kit, and the kit, includes the actual display. It looks a lot like the original one that's used in here, and you'd think it'd be a direct replacement, but unfortunately it isn't. So not only do you get the display, you also get well, this is just some like double-sided tape to adhere the display to the board that's in there. You also get a few ICs and a couple of a few capacitors in here. Like it's all surface mount stuff. And then you get this little board. So this little board is necessary for interfacing the original board in here to the new display. And of course, that's the first thing we're going to do is we're going to do the physical replacement of this. But I'm also going to talk about what this board does, why it does it, and how it actually works. So got everything here that we need to do this replacement. So we're just going to go ahead and start with that now. In order to take this apart, there's two screws that are down here. You can see that they're already gone. I already took them out. And then there's two screws inside of the battery compartment. And I've already taken those out. Like all the screws are off of here, so I can just pop it open. So I didn't bother removing the battery lid there. But then after that, we just have to kind of like pop this open a little bit. There's a couple of catches right here on the top, like little snaps, and then so you got to make sure those come out. But we can't just pull this off because there's a little cable here that goes to the little piezo on the back there. That's the one that does all the beeps and boops and whatnot. So got to make sure not to damage that. Now inside of here, normally we'd have a little screw down in there in the middle underneath this 11 amp fuse there, but I already took that out. So the only other thing I need to do is to pry the board up here. It's got these little snaps right there, so I just have to kind of like pry up a little bit like that one side, pry up a little bit here on the other side, and that frees the board. And now I can just lift this straight up and it comes out like that. Now, unfortunately, the little range knob here that should be normally attached here, mine's a little loosey-goosey now, so it doesn't quite remain attached there. But once it's all put together, it does work just fine. I'm just going to go ahead and leave that there, make sure it's in the right orientation. And so we have the part that we're interested in here. Now there would be normally 4 more screws attaching this board to the main board, but as you can see, I've already removed those as well. And then this is just got a little header up here at the top. Just needs to be pulled straight up like that, and it comes right out. Now we can set this other board aside. Don't need that at the moment. And this is what we're going to be looking at. Now, as I was saying, you'd think that you'd just be able to swap this out. It's got the same number of pins. The pin out for this is, identical to this. This one uses an SSD 1303 driver, and this one uses an SSD 1309 driver. And while if you look through the data sheet, they look almost pretty much identical, there are a few important differences, and that's the whole reason why we need to interface the new display to the old board using this other little kind of in the middle board. And this board, as you can see, has 2 ICs, actually 3. The little one there is a little SOT 235, a couple capacitors. And so this is going to solder onto the board right there. You can see that there's contacts on the opposite side. And then the new display is going to solder onto that little strip right there. So I actually reverse engineered this little board. So we're going to see the schematic for it. And then we're also going to take a look at Logisim, little simulation there, so I can show you what exactly it's doing, and and we'll also go into the data sheet so that you can see why it needs to do it. So let's set all this stuff aside, and we're going to go ahead and start working on replacing the old OLED here. Okay, originally I was going to try to do this with hot air, try to heat those up while I used like a little sharp pick to try to lift up the ribbon. But there's foam that's like directly underneath this area here that cushions the display to this board a little bit, and I'm worried that it's probably going to just end up melting. So I've taped this down to my workbench here, and I'm actually going to use a soldering iron with the pick as well, and just kind of go along and like lift it up as I go, and hopefully that works. I'm going to try not to damage this, but we'll see what happens. All right, so here's a little pick I'm going to use. I'm actually going to stick it down in here where I have a little bit of a gap, and I'm going to kind of just run it down here so it puts a little bit of upwards pressure on there. And now I'm going to start heating these up and moving the pick up as it go along. Oh yeah, that seems to be working pretty well. Come on. It's still sticking right there. It tore. Well, let's try adding some solder here, and then I'll run it along that way. Maybe this will help. And I mean, if you're not really trying to salvage this thing, you can just probably just tear it off. I was trying to, but it looks like it's not going to matter. So, yeah, I should have added solder first. It's a lot easier to lift it up that way. It's lifting up quite well. Now, there it goes. All right, so fortunately, not quite what I was hoping for, but it's off now. So now I just need to clean up all these contacts here. And we're going to use some flux here to help with the process. All right, let's there we go. And now let's just wick all the excess solder that's still left on there, going back and forth. And want to go up across because I don't want to damage all these pads. Okay, and then let's just clean this up. Okie doke, that's good enough for that. All right, now using this plastic pry tool and a little bit of hot air, I think I was able to soften up the adhesive underneath just enough that it's actually lifted. And you can see right there in the corner, or in the edge, that it's separating from the adhesive there. So I just have to keep it on there, keep prying away. I didn't want to use anything metal because I don't want this glass to shatter all over the bench here. But it's almost off. Oh, right, there it goes. Yeah, and this foam didn't really take like any damage. Looks good. Okay, now to put this new little board on, first thing I want to do is I want to get it uh, solder down on there, and then I'm going to put the rest of the components on. Got to make sure not to block these holes right here because that's where the stand-ups are. So it needs to kind of like stay away a little bit. I'm going to leave a little bit of a gap right there where I can apply the solder to, and hopefully it should flow underneath to the rest of the pins there, because I don't want to put like solder all the way across and then have to try to like tack it down. So I'm going to start by putting like a little bit of solder on some of these pins here in the middle. Maybe just a little bit like that. There's a better view of that. Now I'm going to try to get this on here and aligned. I need to make sure that all of these pins are aligned just right. And as I said, I want to leave a bit of a gap right there. So that right there looks like it might be okay. I'm going to try to melt these 3 pins that I applied solder to. Oof, that's not working out too well. Let's apply some flux. See if this works. Okay, so that's somewhat tacked down. I don't want to twist this too much because I don't want to break the bond there. But I'm going to use a smaller soldering iron tip to like basically drag the solder all the way down to try to get it to go underneath. And the cool thing is that I could actually test continuity to most of these pins by just checking from here to there, because a lot of these are actually all connected straight through. There's only like a few that go off into the ICs before it goes off to the new display. That actually got me one of these pine soles a little while ago, and I also got a few tips to go along with it. I'm going to try to use this chisel tip one so that I can get it into that little corner there and try to drag the solder straight across, something like that. Okay, here we go. I'm going to start off by putting just a tiny bit of flux down that corner, and then I'm going to get a blob of solder on here, and here we go. Slowly drag it down. All right. I'm going to just kind of hit these spots here. Drag out, drag out, drag out. Okay, so the cool thing is it doesn't look like I have any bridges, and this actually feels pretty solid. Like I'm not trying too hard, but I can't like get it to sort of like rotate back and forth. So I think that's going to be pretty good. Okay, well, I already have an issue here. Even though this first pin is the first pin on each side is actually not used for anything, it is still a good test to see, like, what is making contact across. But so this one here, unfortunately, did not solder underneath. How about the second one? It did not. So, okay. The third one, yes. Fourth one, nope. Okay, so I'm going to go through it once again, and I'm going to flood them all with solder. Maybe there just wasn't enough solder once I got to the end here. How about this side? Let's check this side. First one, yep. Second one, yep. Well, these two were connected in parallel. I don't know if you saw that when I was cleaning it, but third one, yep. Fourth, fifth, sixth, seventh. Yeah, so I think it's just because when I was dragging the solder, there wasn't enough to completely fill all of these. So I'm actually going to take another little drop of solder on this side and run it all the way across in the opposite direction. And that should hopefully take care of the rest of these pins. It took a few tries on some of these pins, but as you can see, it's all nice and flush. I have no bridges. And the only pins that really go to anything other than just straight across are pin 18, which is like right here. And pin 18 goes to pin 8 and 9 of U1 on this side here. So as you can see, that's working. And then pin 3 of this same IC goes to the other side, pin 18. So it's like right there. So that's working properly. And then the other pin that doesn't go straight across is pin 20. So that would be 18, 19, 20. That one goes to pin 12 of U1, which is right here. So that's making contact. And it also goes to pin 2 of U2. So as we can see, that's working totally fine. So no problems there. This should work. Now it's just a matter of putting the rest of the components on. I'm going to start with the capacitors. It came nicely labeled here, 470 nanofarad. And it comes with 3, but the board actually only uses 2, so I guess just included an extra one. So I'm going to start with this one by just putting a little tiny blob of solder on one of the pads. Let's bring in the capacitor here and tack it down. There we go. Cool. And then just solder the other side. It's just a tad offset, but that's not too bad. That's fine. And the second one, I'm going to try to get this one a little better here, positioned. Okay. No, don't lift. Okay. And there we go. Ah, that one moved. All right, I'm going to have to fix the alignment on that one just a little bit there. I don't like the way it looks. I mean, it'll work, but it looks kind of bleh. Let's put this SOT235 IC here now. Just going to tack over one of these. And this little device is actually just a single AND gate. We'll take a look at it when I show you guys what the schematic for this little board actually is. And that does not look all that great. Gotta fix it a little bit. No, come on. Okay, I'm gonna tack the rest of it down now that it's aligned. There we go. That's good. U1 is a quad OR gate. Okay, and I'm pretty happy with the alignment on that, so I'm going to go ahead and tack down the rest of the pins. All right, that one's done. And now U2. U2 could be doing this. You know what? This capacitor's driving me crazy. I'm just going to try to fix it real quick. That's somewhat better. All right. Okay, got that one. Ooh, I don't like that. Look, it goes right underneath the pins. So that means that this is not sitting very flat. Let's fix that real fast. Let's see. Yeah, that's better. There we go. Okay. That's all the capacitors and ICs done. So far, that's looking pretty good. I like it. Nice thing about this original board is that it has these alignment marks. So it's going to be very easy to get the display to, kind of sit where it needs to be visible on the front of the meter there. So definitely nice that they put those little marks there. Just going to wipe this down a little bit just to get any dust off of it. Just kind of dust it off. And I'm actually going to apply that double-sided tape to the foam, and then that way I can kind of guide the display down and try to, get the best alignment possible so that it's not all like skewed and then I have to try to pry it back up and possibly break it or something. So just avoid all that headache. Okay, well, I'm going to put it down like this. Just going to peel it back a little bit like that and start trying to lay it across. Use the tweezers to help me out. Pull the tape out. There we go. Maybe I'll just do 3. Got like 6 pieces, but I think if we do like one in the middle, and then one on the opposite side right there, that should be good. Ugh, that alignment's a little rough, but I mean, it doesn't matter for this part. It just needs to hold the display down. Okay, not my best work, but it's just double-sided tape. All right, let's clean the back side of the display. Don't want my greasy mitts here leaving a bunch of residue on there that's going to cause it to not adhere very well. And try to get some of this dust off while I'm at it. All right, I think that's about as clean as I'm going to be able to get it in my conditions here. So let's bring this over, and first of all, got to peel all these liners off, and that's peeling up everything. That's not what I want. Come on, now you can do it. There we go. Alrighty. Okay, trying to get this thing aligned. Let's see. I'm going to have to try to look at it from overhead, so I'm trying to do my best here. Got that little corner on the bottom here aligned. Try to get the opposite corner up here aligned, and the other two. Oh, hey, that looks pretty good. Oh, yeah. Look, corner, 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 and corner. Now I'm just going to push down on it a little bit, squeeze it down like that. Yeah. So far, so good. With the interface board completed and the display double-sided taped to the piece of foam, we are ready to solder the ribbon from the display to the interface board. And right now, as you can see, it's just kind of there, but I put a piece of Kapton tape after I just sort of aligned the display there so that it holds it like, in a fairly consistent position there, so once I solder it, I don't get like a really crooked ribbon cable. And it actually helps a lot because it makes it so much easier to just be able to hold it down this way. And then I'm going to start by soldering like each side first, and then that way the middle should stay like pretty flat, and then I'll be able to just kind of solder across the middle. So I've already got the soldering iron hot. We're going to put some flux on both ends, and then I'm going to take some solder that I'm going to apply directly to the soldering iron, and then just kind of tap it on both sides there, and hopefully things should go smoothly. So let's go ahead and do this. Okay, so let's get a bit of flux going on in here. Try to get it to spread out a little bit. I don't want to do too much because I don't want there to be like a bunch of residue inside of underneath the ribbon there. So now, like I said, I'm just going to put some solder on the actual soldering iron first. Try to hold this down, and then just tack it there. The ribbon itself has some little holes there that, like little vias, that will help the solder just kind of wick through. So yeah, that side looks pretty good. I'm actually going to flip it over this way because I'm holding the soldering iron with my right hand. I'm going to push this down with this little pick here, and same thing, just kind of tack it down and let the solder wick through those holes. And maybe if I kind of hold it here, I can actually get this to sit a little flatter. Yeah, there we go. All right, I'm going to go back to the other side and do the same thing just to get it to tack down like as flat as possible. Yeah, I felt that go down just a tiny little bit, so that's a better, a bit of a better fit there. Okay, cool. So now we can peel up the rest of this Kapton tape, and the rest of the ribbon is now sitting nice and flat because it's being held by the two sides that I've already tacked down. Oh no, it started pulling the screen protector off. I don't want to do that yet. All right, that's good enough. It's back on. Okay, so same deal. Apply more flux across and tack it all down with solder. And a little bit of solder here is going to go a long way because there really isn't much required to solder the ribbon to the board since it's all like really flat. It just needs to sort of like wick underneath. This side here is a little light, so I'm just going to barely kind of just put a little bit there. There we go. And cool, that should do it. Just going to clean off some of this excess flux here with the little bit of alcohol and a swab. All right. What do you think? I actually really like how that turned out. So, yeah, definitely happy with that. Okay, now something I don't know if I mentioned earlier is that while this display should be like a really good replacement, it's actually not a perfect replacement. And there's something that this display needs that unfortunately this board does not do. We're actually going to see what that is once we turn it on. And then, as I mentioned, we're going to kind of go deep into the data sheets, and I'll show you why it does what it's doing and what would need to be done to rectify it. But let's go ahead and install it. We're going to try to power it up, and if everything here is good, this should work. I have not been able to see the display on this screen or, been usable in, actually, it's been a few years now. So I'm pretty excited. Okay, before I actually screw it all down, let's just go ahead and give it a test run. And I'm not even going to take off the screen protector just yet, just in case I need to do anything. Alrighty, here we go. Moment of truth. Is this going to work? Place your bets. And here we go. 1, 2, 3. Oh, it's working. And it's not yellow. This one's like white. But this is what I'm talking about right here. See these little pixels that are lit up right here and down here? They're not supposed to be there. The problem is that this replacement display, the way the pixels are arranged in the memory, they're shifted over in a way that once the microcontroller in this writes to, whoa, what happened there? Oh shoot, I just realized the battery's not making very good contact because I haven't screwed it in yet. But anyways, let's turn it back on. So what's happening is the micro in here is writing to the display in a way that it thinks the display is supposed to draw it, or the way that it was programmed to draw it. But this display is a little bit different in the way its memory is set up. So when the micro here writes to this display, it unfortunately sort of like it goes and it wraps around. And so these pixels here are supposed to be on this side, but because of the way, like I said, the memory is set up on here, these end up coming over to this side. So we'll explain that more in the data sheet, but oh man, just the fact that I'm going to be able to use this thing again is like, yeah, it's freaking awesome. So I'm super happy and stoked about this. All right, let's go ahead and put up the rest of the screws back on. Okay, so first the 4 that go onto the front of the display board. All right, so that's all 4 of those on, and let's do the thing. Oh, shoot. Yeah. All right, that's that. And then the 1 screw that holds the board to the front of the case. So that's all nice and secure. Piezo connector back in. Back cover snap on. Take that off so we can get to the 2 screws in the battery compartment. Alrighty. There we go. Awesome. You know what's sad? I just found out immediately after I finished putting this thing together is that there's replacements being sold now on eBay that actually have the display that's actually like correct for this meter, so it doesn't, it's not offset like that where it's got pixels on the other side, and there's even like an LCD type replacement. So I actually bought this. It's been a while since I bought this kit, and it was pretty much the only thing I could find at the time. So I I might be investing in one of those other replacement displays now. Just I mean, it works. It's not going to be that much of an annoyance, but just the fact that it's got those there is kind of like, you know. So yeah, you can get better replacements now, and these instructions are pretty much, I guess, kind of outdated now. But yeah, you know, what are you gonna do? Now that the display is installed and it's all working, let's talk about what that little green board that sits between the display daughter board and the actual display does, how it works, and why it needs to do what it does. So first of all, let's take a look at the schematic for it. And this is it right here. So we've got 2 sections here. We've got this part and we've got this part. This side here, that's the interface coming from the multimeter, and that's where the original display would have soldered to. And all these pins match exactly what the pinout of the display is. On the other side, this is where the new display connects. And as you can see, pretty much everything here is identical to everything on this side. This section in the middle, that's the new little board that sits between the 2 components. So we can see that here we have a 4078. This is an 8-input NOR gate. This here's a 4071, and that is a quad OR gate, and that's a 4071. So that contains this gate, this gate, this gate, and this gate. And that little SOT23 device, that's a single NAND gate. Now, if we take a look at all of these lines that run between the display daughter board and the actual display, we can see that the majority of these lines just run straight across, with the exception of pin number 18, which is a read-write. We see that this one goes up and to the inputs of both inputs of one of the OR gates, and then the output of this string goes back out into the new display. Now, how do these work? Well, when either side of one of these OR gates is high, the output's going to be high. And because these are tied together, when this line here is high, this is going to output a high. And because now it's high on both of these, this one's going to output a high. And now because there's a high on these, this is going to output a high. And if it's low, then the opposite happens. Low, 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 low. Just like Shuddy got. So at first glance, this would appear to be doing nothing. Like it's just basically buffering the signal. Well, then why is it even needed? We could just hook this straight across. Well, I'll show you why here in a little bit. Now, the second line that's tapped off and does not go straight across would be data 0, which is pin 20. That comes here, goes down into one of the inputs of the 8-input NOR gate, but it also taps off and it goes into one of the inputs of the last of the OR gates. And then we see that the output of this OR gate is the one that goes back out into the data 0 line of the new display. And then these other lines that are coming down to these components, they're not severed from going straight across. They're just tapped off. So basically whatever signal is going out to the display, these are also doing something with that data and outputting a certain result that then gets fed into that OR gate, which is the one that's going out to the display. With some trial and error, we could probably figure out what all this is doing and why these are tapped off and what it does when it receives a certain value of data on the input. But we don't need to do all that because I already did all the hard work. And I put together a circuit that we can simulate using Logisim. And here we're going to be able to see what happens at the OLED display, which is represented by these 2 7-segment displays and this set of 8-bit registers right here. This portion with this counter and these 2 ROMs is basically a representation of what the multimeter microcontroller is sending out to the display. And then some other stuff that we have here. We have a reset. I have a load button, an up and down counter, or a switch to count up and down, which some of this stuff we're not actually going to use. It was just for when I was testing this thing out to see how it worked, because I had never used Logisym before. So I kind of had to figure out how a lot of this stuff worked, like on the fly. And there might be a better way to do here what I'm doing, but this is what I was able to figure out. So we're also going to ignore these dip switches here. This was just, I just put it there for testing so I could kind of step through things and make sure that things were working how I wanted it to work. But anyways, as we see, we have a counter. This is an 8-bit counter. And what this is going to do is it's going to start counting from 0. Right now there's a 1 here because if I hit reset here, I can't cause this to reset to 0 unless the clock is working. But so we'll just ignore that for now. As we can see in this ROM, we have some data. And what that's going to do is as the counter steps up, it's going to increment the value at both of the inputs of both of these ROMs. And it's going to cause the ROM to step through the data like sequentially. So when this is at position 0, this one would be at position 0. Now that this is at position 1, this would also be at position 1. And we see that here I only have zeros, and then there's some ones right here. So what this ROM is doing is it's actually controlling the data and command line going into the interface board between the daughter board and the display. And that would be pin 17 right here. As we can see, that one goes straight across, but it's also tapped off. So that's this right here going into the 8-input NOR gate, but we can see that it's also tapped off here to signify that the display is getting a command or a data type of byte. These here are what would be sent from the multimeter into the display normally. This is the data that the multimeter uses to initialize the display and set it up. Now, as you can see, I have 6 7-segment displays up here. These 2 are the ones that are showing what kind of data gets latched into the OLED display. This one here shows what's coming out of the multimeter microcontroller. And these 2 here are showing what happens to the data after it's manipulated by some of these gates. So I'm going to hit the start button up here. And then I'm just going to hold the reset button down so that we can start seeing what happens from position 0. And take a look at what happens up here on these 7-segment displays. Okay, so I'm holding down the reset. As you can see, we're starting off at a value of 0 on the counter. And both ROMs are at the 0 address. And as I release reset, it's going to start incrementing upwards. And pay attention to what happens to those displays. Ready? Here goes. Did you catch it? Now, one thing I want to point out here, this A0, A1, A0, A1, A0, that's not data that's actually sent from the microcontroller to the display. That was just something I threw in here for testing purposes. And as we can see, those correspond to line 18 here, which also has 1, 1, 1, 1, 1, 1. Okay, if you didn't see what happened up here, I've already sort of fast forwarded a little bit and take a look at what happens as we step through the data like a little bit at a time. I'm going to manually step the simulation here by pushing this little button up here, and then we'll talk about it as what's going on over here as we go. So I'm going to click it once. You see nothing really happens. I'm just going to kind of click it at a slow pace there so you can see what's going on. So click, click. We see here that the data coming out of here is 0. All the lines turned low. Over here we have 0, 0. Over here we have 0, 1. And that's because there's a little bit of propagation delay between the signals coming into here going through each gate. So even though this is correct, like we have low, low here going into this NAND gate, the output should be high, which it is. Over here, the output is low going into the OR gate. We see that the other output is low. So the output here should be low. But as we mentioned, there's going to be a little bit of propagation delay. So we're going to see that once we advance the simulation a bit, then this line will finally turn low, and this value is going to match this value. So I'll click it a few more times, and there we see that this changed to low, and now these two match. But this here is still saying D3 because this data has not been latched into the registers. we'll see that once this clock goes low and it goes back high, that the data is going to latch. Okay, so I misspoke. It's when the clock goes low, the data gets latched. But we saw how there was a bit of a delay there, and you may have also noticed how there's a bit of propagation delay going through these gates. So let's keep stepping through it until we get to this portion here. Okay, now we see that we've reached the value of A0 here in the ROM, and we still have a command being sent out to the display. So let's step through this a little bit more. Now we see we've got A0 here. This has also become A0 because now it's not relying on this line here changing in order for this value to read 0. It's only taking the first 8 bits, or it's only taking the data from the bits coming in, feeding them directly into here. But now take a look at the output. Oh, you saw that? This changed to 1. Let's click through it a little bit more. Okay, now we have our clock going low. And we see that we've got that propagation delay going on here. Now this clock went low, but that's going to take a little bit of time for the registers here to latch that data. But once the data's latched, now we get A1 here. So why does this here say A0 and this says A1, as well as the data latched into the OLED? Well, that has to do with the way that the graphics memory inside of the original display works versus how the graphics memory inside the new display works. For that particular instruction, where the original display required an A0, the new display requires an A1. So the only thing that tiny little board that we installed does is convert that A0 instruction or command into an A1. And the only time it does that is when it's setting up the display to actually display what is being sent to it. It doesn't do it anywhere else. Okay, now I might hear some of you asking, well, what happens if the data being sent out to display graphically happens to be that same A0 value? Well, that's not going to be a command anymore. That's going to be data. So this line here is going to change to a high state instead of being a low state. So now let's take a look at what happens when this A0 is sent out as data. So basically what's going to happen here is we're going to jump down to this line, and these values are going to get sent out as if they were data. All right, here we go. See, as we can see now, A0 gets latched as A0, but again, that's because it's not a command anymore. Now it's data. So we know that A0 turns into A1, but what does that even mean? Well, that's basically telling the display that we want to remap the segments to be column 0 is a segment 0. And this just basically has to do with the way that the memory is arranged inside of the display for the orientation that the display is going to be mounted in. So as for the old one, required A0. In order for the new one to display correctly, it requires an A1. Now the last thing here regarding these 3 OR gates, if it's not completely obvious yet what they're doing, and the term propagation delay hasn't been said enough, that's exactly what they're doing. It's just a little bit of delays. So when the microcontroller asserts the write line to latch the data into the OLED display, what it's doing is it's just taking a little bit longer to do so because the data coming from the microcontroller going out to the display is now going to be delayed just a tad because it's got to go through all these gates. And so by delaying it a little bit, it's allowing time for everything over here to settle before the data actually gets written into the display memory. All right, so the last thing we're going to talk about here is why some of these dots on the new display wrap around to the other side of the display. And I'm going to try to keep this a little bit brief. Like, believe me, if we were to talk about how these displays work and everything that's required to make them work, this video could go on for a very long time. So everything I'm just talking about here is kind of like just the Cliff's Notes of how these displays kind of work. So once again, this issue has something to do with the way that the graphics RAM inside the display is arranged and how the old one worked versus how the new one works. If we take a look at this section of the datasheet here, this is for the SSD 1303, which was the original chip inside the old display. And right here under this section where it says graphics display data RAM, it tells us that the size of the RAM is 132 by 64 bits. The actual display is only 128 by 64. So that means that we actually have 4 extra columns of data that won't actually be shown by the dots on the actual display. If we take a look at the new display, which is an SSD 1309, for the graphics display data RAM, it tells us that the size of the RAM is 128 by 64 bits. So the RAM inside the new display is only as big as the actual area of all the dots that can be lit up. And the reason why the old display has a little bit more RAM than the new display is because the old display used some of this data or some of that RAM for scrolling purposes. So as we can see here, we have segment 0 through segment 131, and that's a total of 132 columns, which would be represented by that 132 by 64. So now you might think, well, why does that matter? Why can't it just ignore the last 4 columns and just display between 0 and 127? Well, while the new display, certainly this would work, the old display doesn't work like that. In order to light up some dots on the display, both of the display chipsets, the 1303 and the 1309, both require 2 types of data to be sent to it. It needs to know which bank you want to write to, which are these horizontal blocks of 8 pixels high each, and it also needs to know what column you want to start writing to. So you can either start like at the first column, you can start somewhere in the middle, you can start somewhere at the end. It doesn't matter. The display just wants to know, where do you want to draw vertically and at what horizontal location. That's done by sending 3 bytes of data. The first byte indicates which bank you want to write to, and each one of these horizontal sections is a bank. And then the next 2 bytes, one is the lower column address, and the next one is the higher column address. We can actually see that happening here in this little bit of data that I captured. So as we can see here, the microcontroller and the multimeter sends a data value of B0, which is then latched into the OLED display by this write line here. So when this write line goes low, that data gets latched. It's almost like the clock signal that I had in the simulation. So B0 correlates to the bottommost bank on the display. So we've selected the bottom row, and now we're going to tell it, or the microcontroller and the multimeter tells it to load a 2 into that lower column register, which is then latches in with that write command. And then it changes that into a 1-0, which is then latched into the higher column address register. So that means that it's going to start drawing on bank 0, column 2, because the way this is arranged, this 2 would be the, as we said, is the lower column address, and this 0 is the higher column address. So bank 0, column 2. And then after that, it basically just writes a bunch of zeros to that entire bank, which is effectively just going to make that entire bank just blank. It's just going to be basically a black display. And we see that it does that not once, twice, 3, 4, 5, 6, 7, 8 times. So that effectively blanks out the entire display RAM. Later on, it gets to this portion, and we see we have 1, but let's see where it drew to here. Oh, let's see, bank 0, okay. And it started at column 2. But let's rewind a little bit here. Let's see where it started drawing on that last bank when it was blanking out the display. Okay, so we have bank 7, column 2 again. And if we take a look at any of these, we can see that it starts drawing at the bank specified, column 2, every single time. So what's happening is that on the original display, that first column of pixels always started at column 2. On the new display, they'll start at column 0. And because there's nothing on that little board that's going to translate between column 2 and making sure that what reaches the actual display we have now is column 0, the display is always going to be shifted over by just a tiny bit. And now you might be thinking, well, then why don't we just subtract 2 every time that it's going to write to the display by detecting when this value becomes 2 and sending out a 0 instead? Well, yes, that sort of would work, but as I mentioned, the display does not necessarily need to start from the first column every single time. If we take a look at this section here, this is actual display data being written to the display, which would include like all the numbers that are on the display, like all these other little elements that it shows. So let's zoom into one of these little sections here. We'll just kind of pick something at random. Let's see. Let's go right here. This looks pretty dense. Okay, let's see where some of this writing here takes place. All right, this here's a good section for an example. So we see right here that it starts writing at bank 2, but it doesn't start at column 0, 2. It starts at column 5, 8. So in order to get this correct, we'd have to subtract 2, which would mean that it would have to start off at column 5, 6 instead. So what the interfacing circuit would have to do in this case is subtract 2 only when it detects that it's a new bank being written to, and that the data that's coming in is column address data, not just data that is going to display on the vertical row of pixels. Now, when I first started capturing and analyzing this data, this thing here caught my attention because I was like, what? That almost looks like it's saying something. And then I realized, oh, wait a minute. And so I started shifting these bits so that the highest bit would be on the top and the lowest bit would be on the bottom, the way that it would be inside the display. And look what happens. You know what it says right there? Yep, it's that www.agilent.com that shows up on the splash screen when you turn on the multimeter. Now you may be wondering why it is that I know so much about these displays, or why I even bothered to learn so much about these displays if I just bought that little board to replace it with. Well, that's because before I bought that replacement board, I was actually working on making my own. So this jumbled mess of crap right here is basically kind of like a prototype I had going on in my quest to try to get a replacement display for this thing, or make a replacement display for this thing. So in here what we've got is I got some chips down there. That I believe that was a latch down there. There's a little PIC micro hiding down there, a little voltage regulator, and an SSD 1309 display here. But as you can see, this one uses a smaller connector. And these are actually sold as these little SPI serial displays. But the actual display itself isn't serial only. It does support parallel communications. So when I found that out is when I started messing with this and trying to basically roll my own thing, to the point where I actually even designed my own little board. The only problem I was having is that the little PIC micro that I'm using in here, I couldn't get it to be fast enough to intake that data and translate it to what the display actually needs to be able to display the pixels properly. So then I thought, well, since this isn't fast enough, maybe I can see about using like an STM32 to do all the hard work. And so I got this Nucleo board that I bought off DigiKey with the intention of, trying to make something with that. But my problem is that I suck at coding. So there was a lot of learning that was going to be involved for me in order to even be able to get like anything working with that. And that's around the time when I discovered that there was already people selling replacements for these things. And as I mentioned, there's some of these units being sold that are basically like pixel perfect replacements. And here's a picture of one from one of the ones being sold on eBay. Look what it's got. It's an STM32. So unfortunately, yeah, I couldn't make this happen, and other people have already done it. But it was still a bit of a learning experience. I learned a lot about these OLEDs and how to drive them and all that stuff, to the point where if I wanted to use one of these in like a project or something, I think it'd be much easier for me to do so now. And well, just as a quick little thing here before we close off this video, I'll just show you basically what it does the way it's set up right now. So I've got 5 volts coming into here at a certain point on the lines right there, and this is where it would interface with the multimeter. while I was trying to figure it out, I made this special cable here just so I could probe all the lines coming from the microcontroller and the multimeter. The rest of this stuff over here, this is one of those little boards that I was using for the logic capture. This here is the DC-DC converter that boosts the voltage from 3.3 volts up to the 12 or 13 or so that the display requires to be able to light up all the little dots there. So I'm going to apply 5 volts now. You're going to see what shows up on here. This was just basically like my own little testing that I had going on. So as you can see, it says TWB, 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 like just repeatedly. And that's because at the time that I was working on this, it was back when I still was using the old channel name. So yeah, I just wrote a little bit of that data there that's writing to bank 0, starting off at column 0, and just writing a few TWBs across. So that's going to do it for this one. As I said, to go into depth on these displays would certainly require more than a few minutes. But if there's some interest in me doing so, I'd certainly be willing to do that. Although I think that I'd be better served if I wrote up a script for it, because there's just so much to talk about, and some of the stuff is not all that important, but there's things that are. And when I do these videos where I just kind of like talk it out of my butt, there isn't really like any sort of structure that I use. It's all off the cuff, basically. None of this is scripted. Pretty much all my videos aren't. But yeah, I don't know. Let me know. So if you made it this far, thanks guys again for watching. I appreciate you staying this long, and I will see you all around the bench.